Now that is geometry. So you dealt with algebra at home. You did the Taylor series for a function of two variables. So since you said you don't have any questions, I will just quickly remind you the Taylor series. Once you fix a point, right, and the Taylor series shows up only if you fix a point x0, y0 in the domain, well then the value of function at any other point is related to the value at that fixed point in a very simple way, very long way though. It's that point plus the partial derivative at that point with respect to x times x minus x0 plus partial derivative with respect to y at that point times y minus y0. And these two terms make the first degree approximation, and there are infinitely many more terms with degree raising, and those terms x and y mixed, sometimes multiplied. But this is algebraic approach of how to look at a function. Now geometric approach is going to be about looking at the graph as a surface in 3D. And there is something special about this graph and the three-dimensional space that you consider. So we agreed upon having the domain, having those x and y variables horizontal, and the axis z vertical. And now, using this agreement, we think of z being the value, and x and y being independent variables, and that brings a special flavor to the geometry. Now, this geometry is a little bit different. The context is different from what we used to have. What we used to have before was the coordinate system in three-dimensional space that is chosen arbitrarily, and all the axes were equally important, right? And independent of anything. We just chose the coordinate system the way we wanted, and then described the object there. Planes, lines, whatever we wanted. In this setup, the context suggests that the z-axis carries a variable z that depends on x and y. So this axis becomes very special, and those are independent of each other, but considered separately from z. So that will bring different flavor to all the equations that we consider in this 3D, and to the surfaces and planes and lines that we will consider. Now, what about physics? What would be a context in physics when we would consider functions of two variables, functions on a plane? Why would you ever assign a number to a point on a plane? What can be this setup? Well, of course, you can think about many different setups. Right? So the one I would choose for now is imagining that the plane is where you have gas, and that gas have different pressure at different points, and then for every point the pressure is the number assigned to the point. And of course, the realistic, much more realistic picture would be to think about three-dimensional space and gas filling up the three-dimensional space and pressure of gas at points of three-dimensional space. We are not ready yet to look at functions on three-dimensional space, essentially because geometry will be lost. We will not have extra fourth dimension to put the z-axis on, so that the values of pressure can be mapped to that extra fourth dimension. So we will have to limit our dimension and think of gas being flat and having pressure there. But still, pressure can be high at some areas, low at some other areas. And if so, then gas behaves a certain way. So we have some expectations about behavior of gas. If the pressure here is high and the pressure there is low, then we expect something to happen, right? We expect wind to blow, right? Which way? That way? Do you have any expectations of how wind blows? Yeah. This is high pressure, this is low pressure. From high to low, right? So it will not blow arbitrarily, it will blow a very predetermined way. And that expectation can be, well, we will try to look at what goes on and test what goes on against this expectation. So these are going to be our primary points of view on a function of two variables.